Hi guys, welcome to today's lesson. So we've looked at so far the concept of circles. We looked at circles and lines. We looked at circles and angles. Now we're going to look at circles and quadrilaterals, right? Remember, a quadrilateral is a polygon with four sides, right? Four straight lines. But now we're going to look at how does it then link to the concept of circles, and exactly how can we then deduce certain relationships based on that. Then in this lesson, one of the things that I'm going to actually do is to actually show you the investigation myself for you to see exactly what happens when I say move this or move that, and what are the relationships that we are seeing there. But let's just jump right into it. So far we've looked at the concept of lines, and now with the lines we're going to look at this concept of what we call a cyclic quadrilateral, because I just said we're going to look at quadrilaterals. That's the main idea that we're going to try and look at in this lesson. Now, have you ever thought about, is it possible to construct a circle around any 3 points, one, that are not collinear, using, you know the drill, the compass, the ruler, and the pencil. Not collinear meaning they don't lie on the same straight line, right, where maybe it's A, B, and C. Rather, it will be points that are like this. So is it possible for me to draw a circle around these 3 points that I have on the board? That's what you need to think about. Right. So remember, collinear is when points lie on the very same straight line. That's what we're talking about. But if they are just everywhere, then we say they are non-collinear, or they are not collinear. Now, to do that, the very first thing that you will need to do is to construct a perpendicular. Remember what this introduces. Remember when we started, we looked at the concept of any line from the center perpendicular to the chord actually passes through the center, right? So you know that. So to construct that, you know you'll need to construct a perpendicular bisector of that line. That's one thing. But also, the perpendicular bisector of a chord, it normally passes through the center of the circle, right? That's what I'm just talking about now. So that means if I construct another perpendicular for this other chord, which is this one here, where they intersect one another will then be the center of the circle, which I will call O. And therefore, using your compass, you will then place your point, your sharp point here, and then your pencil on any point. When you construct the circle, you will see it will pass all 3 points that we have there. Just try it. Remember, the first thing that you need to do is to construct a perpendicular for these 2 points, right? And then the second thing, another perpendicular for those 2 points. Where those two are intersecting with one another, that's the center of the circle. Please try it at home so that you can see what we are talking about there. Now also, if now we have 4 points, what does that then mean, right? Can I still construct a circle around those 4 points that we have there? Let's look at it. Right, so here are my points. Now, I want you to think about what exactly is the theorem that links 4 points to the circle, right? Remember we said if I have 4 points on the circumference of the circle and 2 angles are equal to each other, right, that are on the same segment, then it introduces the concept of what? Angles on the same segment. So that's the concept we can use to try and construct this particular circle around these 4 points that we have that are not collinear to one another. But let's see exactly what do I mean. Right, so an angle subtended by a chord of a circle on the same side of the chord are equal. Remember, that is angles in the same segment. So meaning If I was to join those points such that I have this angle being equal to that angle, I will then construct a perpendicular of this line and then a perpendicular of this line as well, using the very same thing that we spoke about, and then that will then be my center, right? And if that's the case, then my circle will look something like this. I just did not show the constructions here, but remember, the center, you find it by constructing the perpendicular to this one and the perpendicular to that one, or the perpendicular to this one. Wherever they are intersecting, they will then be intersecting at the center of this particular circle. Now, if a line segment joining 2 points subtends equal angles, right, at 2 points on the same side of that, then the 4 points are concyclic. Now I want us to talk about this concept of concyclic, guys. Concyclic would mean all 4 points lie on the circumference of the circle. I will repeat that. Concyclic means all 4 points lie on the circumference of that particular circle, right? That's what it means to have concyclic points. So meaning, if with this particular converse that I have here, if the line segment joining those 2 points subtends equal angles at 2 points on the same side of the line segment, then those 4 points are concyclic, which is this particular case that I have here, as I showed you when you're trying to construct a circle around these 4 points. And then our reason is converse angles in the same segment. Now, our big idea right now is actually to look at a quadrilateral, right? A quadrilateral would then be, a quad is a polygon that has 4 straight lines or straight sides that are joined together. So polygon with 4 straight sides has 4 angles that add up to 360. It may be irregular or regular. The regular one would be things like a square, things like a rectangle, right? Things like a rhombus, but irregular would be just me having any quadrilateral for that matter, something like this. That's an irregular. Me having a quadrilateral that looks something like that. It's still a quadrilateral, though it might look like a kite, but it's just a quadrilateral, as long as it has 4 sides and the angles add up to 360 degrees. And then examples of regular quadrilaterals will be our parallelograms, which are rhombus, a rectangle and a square, a trapezium and a kite. Those are my examples of regular quadrilaterals. And then now, the big idea, remember, is the cyclic quadrilateral. Remember, concyclic, guys, we said that it's when 4 points lie on the circumference of the circle. And then, if those 4 points lie on the circumference of the circle, when I join all those 4 points to give me a quadrilateral, we then say that that quadrilateral is a cyclic quadrilateral. Remember, if 4 points lie on the circumference, they are concyclic. If 4 points are concyclic and it's a quadrilateral, that quadrilateral, we call it what? A cyclic quad. So a cyclic quad would actually be a quadrilateral whose 4 points are concyclic. So that's what you need to think about there. So a drawing would then look something like this, where A, B, C, and D are all on the circumference of this particular circle here. Now, is there a relationship between the size of the interior angle of a cyclic quad? That's the question we are trying to think about, and we are going to try and investigate. Now, with this one, you will then need to try and move these angles around. Maybe let me just try and show you that. So, this is my quadrilateral, right? If I move this point around, do you see? my 114 and my 66 stays the same. But my 116 there, it keeps on changing, and my angle D keeps on changing, keeps on changing, keeps on changing. If I go this side, do you see? Now I have something different. It's no longer a quadrilateral, right? Similarly, if I move this 80 here, do you see? I have the 80 and the 100, they stay the same, but the others are changing as you are trying to move this thing, right? As you're moving this point around, right? So that's the big idea. But now look at what is happening as you are trying to move. Angle D is 80 degrees. Angle B is 100 degrees. When I add them, it's 180. Angle A is 103. Angle C is 77. When I add them, it's 180. Let's see when I move it what happens. I'm at 91 and 89. That's still 100. B and D still 180. Or still 180, I mean. I move it again. I'm now at 100, 80, 180. It's 180, 180. But the opposite angles, please look at that. Let me move this one again. You see, I have 65, 115. That's 180. 180. You move it like that. See, so far, all these angles, they're showing us that no matter how you move it, it will always give us the 180 that we are talking about with the opposite angles. But that's what we are just trying to look at in terms of the theorem, right? So there is a relationship. The relationship is that if I add these opposite angles, I'm supposed to get 180. Similarly, if I add these opposite angles, it's supposed to also give me what? 180 degrees. Right, so you move the point along the circle, and you can see that as you are moving it, I said, look at the angle C and the angle A. You saw that when you add them, it still does give you 180. Similarly with B and D, you can see it normally gives you 180 as you are trying to move it. Now, when angles add up to 180 degrees, we call them supplementary angles. That's the big idea. Guys, remember when you were earlier on doing maths, we spoke about complementary angles and supplementary angles earlier on in the grades of you doing maths, right? That means supplementary add to 180, complementary add to 90 degrees. So that's what we are talking about. But with the cyclic quad, they are definitely supplementary to one another. So that's what we're talking about there. So you can see that even with this one here, 86 plus 94 is 180, 114 plus 66 is 180. You still move the point around, it will still give you the very same thing as what we spoke about, right? So the big idea here is that if I have a circle like this and I have a quadrilateral inside there, when I want to add this angle and that angle, you saw our investigation says that they need to amount to 180. If I want to add that angle and that angle, they also need to amount to 108. But we're going to then try and classify this as a theorem when we come back from the ad break. For now, I want you to think about this. Is there a relationship between these angles of these four concyclic points that form a cyclic quadrilateral? And also, what exactly makes a cyclic quadrilateral? That's what I want you guys to be thinking about right now as we go into an ad break. And as soon as we are back, I'm then going to give you the theorems that have to do with this investigation and our conjunctures as we've been doing with the other lessons. Stay tuned, I'll be back just now. Hi guys, welcome back. So we've been looking at the investigation, right? And now it was great because I actually did even show you the investigation itself. What happens when you're moving around the point? What exactly happens to opposite angles, and what does that mean, right? That's what we've been trying to look at. Now we're gonna pin it down and call it a theorem, because remember, we don't just want to look at and say, oh, this is a theorem, do it. No. We need to try and see, how does it come about? If I move the point around, what happens? Does this stay the same? If I form a conjuncture, will the conjuncture be the same throughout, or are there certain conditions that I need to actually adhere to in order for it to then uphold all the time? It's those things that you need to think about. But for now, let's just look at this one and see exactly how this becomes then a theorem that has to do with a cyclic quadrilateral. So the summary of our observation is that the interior angles, right, these angles must be inside the quadrilateral that are opposite each other. The other condition is they must be opposite each other. They will add up to 180 degrees. So meaning, if I have that and then I have quadrilateral like this angle and that angle there, let's call this x, let's call that y. My x plus y must be equals to 180 degrees, right? Let's call this one a here, let's call this one b. Also a plus b must also be equal to what? 180, provided that my quadrilateral is concyclic, not just any quadrilateral, and also provided that my angles are interior, so are inside the quadrilateral that we are talking about. Right, with our investigation, remember we saw that if I add the 94 degrees plus the 86 degrees, if you don't really, if you're not so good in terms of your mental math, just quickly press your calculator. You will see that this will be 180 degrees. Similarly, with 104 degrees plus 66 degrees, this will definitely be equals to 180 degrees. That's what the theorem is actually saying to us. Now, the opposite angles of a cyclic quad are supplementary. That's the theorem, right? Opposite angles of a cyclic quad. Now, with this one, I always get people asking me, exactly, if I have a quadrilateral and it is not concyclic, is it then a cyclic quadrilateral? If this property holds, yes, it is a cyclic quadrilateral. So the fact that I say the definition is, it does not make it to always just be that fact, right? To define something does not necessarily mean that if it is not inside a circle, then it's not a cyclic quadrilateral. No. What makes it a cyclic quadrilateral are the properties that hold for a cyclic quadrilateral, and this is one of them. So please think about this, right? I know that if I was to give you a quadrilateral A, B, C, D, and there is no circle around it, and I say to you, prove that this is a cyclic quad, you will quickly say it's not a cyclic quad. Why? Because the 4 points are not concyclic. No, that's not the fact, right? The fact is, your cyclic quadrilateral, yes, its description and its definition is that it's when the 4 points are concyclic, but that's not really what makes it to be a cyclic quadrilateral. What makes it to be a cyclic quadrilateral will then be the properties of it being a cyclic quad. So it doesn't really always have to be concyclic, no. I will show you what I'm talking about as well at a later stage, right? And then our reason is we normally just say opposite angles of a cyclic quad. Some people normally write C/Q to represent cyclic quadrilateral. That's really still acceptable for you to write. And then the converse, what do you think will then be the converse of this, right? I said the opposite angles of a cyclic quad are what? Are supplementary. What do you think is the converse of this? I will just give you a second to think about this, right? Yes, I can see you're thinking it there. To say the converse of this will then be, if the opposite angles of a quadrilateral are supplementary, then the quadrilateral is what? Is cyclic, right? So you need to think about that. And this will be converse opposite angles of a cyclic quad. Now let's talk about this. What am I trying to say? Converse is when I did not tell you that this is a cyclic quad. But because of the fact that if I add the angles that are opposite in that quadrilateral I had given you at the time, and I find that it is equal to 180, then that qualifies that quadrilateral as a cyclic quadrilateral. I will repeat. If I give you a quadrilateral and I did not specify that this is a cyclic quad, and I ask you to prove that it is a cyclic quad, one way of doing that is to look at the opposite angles and find what are the angles or values or the size of those angles. If you add them and you find them to be 180 degrees, then therefore, conclusion, ABCD is a cyclic quadrilateral. Right? So I don't always need to tell you that it is a cyclic quad for you to know that it is a cyclic quad. No. If you can add the opposite angles, add them to 180 degrees, then it is definitely what? A cyclic quadrilateral. So those are one of the things that you please need to think about. And when we use the word converse is when we were not told that it is a cyclic quad, but they required us to prove that it is a cyclic quadrilateral. Right? And then what is the relationship between the exterior angle of a cyclic quadrilateral and the interior opposite angle, right? So I'm saying, what is the relationship between this here and that there? I want you to think about that, right? I'm going to try and show you a proof of what this is about, but that's one thing that you need to think about. What is the relationship between angle B and the angle CDE? What is the relationship between the two? That's what I want you to please be thinking about right now. So let's look at this, right? What do I know from this thing that I have here? Just think about it. What do I know? I know that one, I will say given, right? I know that A, B, C, D is a cyclic quadrilateral. I know that because the 4 points are concyclic. I don't necessarily need to prove it at this point in time. Why? Because already I can see the 4 points are on the circumference. That's what I know. Also, I know that AD is produced. Now I'm introducing another word. Produced, please, it's not about manufacturing or producers as we know them, right? Produced to E. Right. In this context, in mathematics, when we talk about something being produced, we are saying it's been extended, right? If I say this side is produced to something there, it means I drew a line from the end point of this line and joined it straight. But if I just join it like this, I didn't produce anything. Producing it, it means it must be straight with the initial line that I had when I started. That's what producing means in this in mathematics context, by the way. So I know these two things already from that thing, right? Given that this is a cyclic quadrilateral, I know that angle B plus angle ADC is equals to 180 degrees. Why? It's opposite angles of a cyclic quad, right? I know that. And given that I know this fact, I also know that, but my ADC plus CDE is equals to 180 degrees. Why? Adjacent angles on a straight line. Right? Adjacent angles on a straight line. I do know that if I was to add this angle here and that angle there, they must give me 180 because it's a straight line, right? So both of them, you can see that it means that B, therefore it means that B plus ADC is equals to ADC plus CDE, right? And given this, the ADC and the ADC, you know, it's one and the same thing. It means that, therefore, my conclusion will be angle B is equals to angle ADC. Not ADC, angle CDE, right? So I'm not writing the correct thing there, sorry. Angle CDE, right? So what am I trying to say? This angle here and that angle there are going to be equal to each other. Because of this proof that I've shown you here, when I was trying to tell you that I know that this is a cyclic quad and the line is produced. Because it's a cyclic quad, it makes these two angles here to be supplementary to each other. But also these two angles are also supplementary because it's adjacent angles on a straight line. And therefore, it then gives me those two angles to be equal. So what is the theorem here? The theorem that is that then the exterior angle of a cyclic quad is equal to the interior opposite angle. So in this instance, this is what I mean, guys. You can only have an exterior angle if one of the sides is produced, right? If one of the sides is produced, only then, and I mean only then, can you have an exterior angle of a cyclic quad. So I produced this line there. It will then make this to be x there, and that will be x as well. So how do I then have an exterior angle? I know you are thinking it. Only and only if one of the sides is produced. The same thing with an exterior angle of a triangle. You know I can't talk about an exterior angle of a triangle unless I have one of the sides being produced. So you need to make sure that you understand that one side must be produced in order for this particular quadrilateral to have an exterior angle. One side must be produced for a triangle to have an exterior angle of a triangle. So those are the things that you please need to note there. So our reason for this is normally exterior angle of a cyclic quad, or you can say exterior angle of C/Q, right? And that's what I will then have as the theorem there. And the converse of this is, if the exterior angle of a quadrilateral is equal to the interior opposite, then the quadrilateral is what? Cyclic. So what do we mean? If I have, I don't even want to draw it in a circle even. Let me not draw it in a circle. If I have Let me not draw it in a circle, because then you will think it's only when it's inside a circle do we then have a cyclic quad, right? If I have something like this, right, and this, I find that this angle here is x and that angle there is also x, then it makes A, B, C, D to be a cyclic quadrilateral. That's what the Converse says. And then, you know, your reason, you will include the word converse exterior angle of a cyclic quad. This is when you do not know and they did not tell you that this is a cyclic quad. They just said it's a quadrilateral, but I know that one of the sides of the quadrilateral is extended or produced in mathematical terms, and the angle that is formed there, which is the exterior, is actually equal to the interior opposite angle, right? Let me even show you. Exterior angle, which is this, is equals to the interior angle there, opposite angle, right? Exterior is equals to interior opposite. Exterior is equals to interior opposite. That's what you please need to be thinking about going forward there. And then my reason will include the word converse. Why converse? Because we did not know that this is a cyclic quadrilateral. So far, what did we look at, guys? If opposite angles are supplementary in a quadrilateral, that's a cyclic quad. In a cyclic quad, opposite angles are supplementary. Or an exterior angle of a cyclic quad is normally equal to the interior opposite. Or if an exterior angle of a quadrilateral is equals to the interior opposite, then that quadrilateral is then classified as a cyclic quadrilateral. Guys, I hope you're having so much fun as I am right now, because really, I know that Euclidean geometry is viewed as the complex topic, but I promise you, if you take time to learn it and practice it, you will always get it right. I promise you that. For now, let's quickly go to an ad break, because I feel like, hey, we've now digested a lot of information. So we need to sit down a bit and let it sink in so that we can come back and answer some questions and try and put this into context. I'll be back with some more. Stay tuned. Hi guys, welcome to the last segment of the show. So guys, we've really been doing some great stuff here with our circle geometry. We looked at some circles and quadrilaterals and exactly how do they link to one another and what are the relationships inside a quadrilateral, provided it has a circle in it or the circle is around it. What are these theorems that we are trying to look at, and exactly what would then be the converse of it? So if I do know that this is the case, what conclusion can I draw? If I don't know, what conclusion can I draw? All of those things, right? So right now, we're actually going to try and see how do I then link this to questions, right? I'm going to try and show you a few questions where you get asked to solve certain things based on these theorems that we've done thus far. So let's just have a look at it. But before that, I have some exciting things that I want you to first think about, some deductions I want you to think about based on the previous theorems that we did with our previous lessons for circle geometry. Let's just try and look at it, right? So here, when we are applying these theorems, I want you to think about what deductions can you then make from this diagram. And also you need to then give me reasons why you are claiming what you are claiming. Because remember, I told you, we do not do something because it looks like it or because we think it is it, without having proof for what we are talking about or having a foundation. That's why we start with these theorems and then apply them later on. So what deductions can we then draw from this, right? So if you look at what we are having in this particular diagram of mine, clearly you can see that if I add these two angles, I definitely will get 180 degrees, right? So the very first thing that I'm going to say is AB, or rather, let me not use that one. Let me do this. So we'll start by saying first, we know that angle B plus angle D is equals to 180 degrees. It's not that I'm saying it because it's a cyclic quad. No, I'm saying it because you can see that I can add these angles here and get 180 degrees, right? So meaning this is my 86 degrees plus definitely 94 degrees, which is then equals to 180 degrees. So I'm giving it as 180 based on that, right? But now, more interestingly so, what you can then see is I have a 90 degrees here, I have a 90 degrees. Yes, clearly when I add them, I'm going to get 180 degrees. But this is where I want to actually draw your attention. If I was to draw a line through here, what deduction can I then say? So if we are looking at that red line that I just threw there on the board, you need to think about what can I then say? And I know, I can see you guys that you know what I'm talking about, right? So that line is gonna then be called the diameter. One, why is it a diameter? Because remember the theorem that we did, we said a diameter subtends a 90-degree angle on the circumference, right? So on either side of this particular line that I just drew now, we will then say that what? Those angles are 90 degrees, therefore the line, in this instance, the line BD will then be my diameter. So line BD will pass through the center of the circle. So that's one of the things that you please need to be thinking about. That's one of the deductions that I'm going to draw from this. So let's see exactly what do I mean. So I will say BD is a diameter, right? I will just say or rather let me write it in full, diameter. And the reason why this is actually a diameter, why? Is because angle in semicircle, I will say SC, right? Why? Because you can see that this angle here is a 90 degrees and that angle is a 90 degrees. And normally you know that a diameter subtends a 90 degrees and a diameter subtends a 90 degrees. The other deduction I know that somebody might say there is ABCD is a cyclic quadrilateral. Really, that you can say is a deduction, but it's not really a deduction. Why? Because already the 4 points are on the circumference of the circle. So given that they are on the circumference of the circle, I can't then really say it's a cyclic quadrilateral. No, they are on the circumference. So that means it is a cyclic quadrilateral. So it's not really a deduction. Right? A deduction will be something that if you were to do this, then you will find this. But in this instance, ABCD, though, is definitely a cyclic quad. Why? Because the 4 points are concyclic. So that's what you need to think about them. Now let's look at more interesting questions to do. It says, in the following sketch, BC is parallel to DE, right? So I have BC is parallel to DE. So this line here and that line are parallel to one another. And if they are parallel to one another, it definitely makes this angle to be equal to that angle, raising alternate angles, right? And then we can try and talk about certain angles or certain things under there. and we are given that A is 130 degrees, and then they want us to find the size of C1 and F. So I want to come to the side. So let me use maybe a more colorful color here. So we agreed that this angle here is equals to that angle there, right? That's alternate angles. Given that this is 130 degrees, we know that this one here, this quadrilateral here, the 4 lines, they form a cyclic quadrilateral because the 4 points are on the circumference of the circle, making this to be 50 degrees. So already, I'm not answering questions as yet. I keep on saying to you, I'm only looking at what can I do on this diagram based on the statement, right? If that is 50 degrees, this one is also 50 degrees. Why? Because they are alternate angles. And if that is 50, then this will be 130 degrees. You see? So that's what I have so far as the additions that I can make based on the fact that I know that this is those lines are parallel, and also there's a cyclic quad and all of that. So firstly, angle C1, I will say that angle C1 is equals to 50 degrees, and my reason for this will be opposite angles of a cyclic quad, right? Remember, I did say that with cyclic quad we normally write SQ to show CQ, I mean, to show the concept of a cyclic quadrilateral, right? And then the other thing that I will then do that they needed me to find was angle F, right? So with angle F, I will then say that this angle here is firstly equal to that, and then link it to angle F. So I will first say C1 is equals to D1, and this is equals to 50 degrees. And the reason for this will be alternate angles. Remember, for you to say alternate angles, you must also state which lines are parallel. That's because BC is parallel to DE, right? I know that. And then from there, I will then simply say F is equals to 180 degrees minus 50 degrees, which will be because of opposite angles of a cyclic quad. Opposite angles of a cyclic quad, therefore angle F will be equals to 130 degrees. I don't need a reason for that, guys. It's just math. I'm just subtracting 2 angles. Also, in the following sketch, ABD, right, as you can see, ABD is given as 40 degrees and ADB is given as 35 degrees. We want to find with reasons the size of C1, right? So firstly, I will then, let me go to the next slide so that I have more space. So firstly, I will say in triangle ABD, right? In triangle ABD, I know that angle A will be equals to 180 degrees minus 40 degrees minus 35 degrees. And this will be because of sum of angles in a triangle, right? Sum of angles in a triangle will be equal to 180. So that's what I'm subtracting there. So 180 minus 40 will be 140 minus 35 will actually be 105. And that's my angle A. But that's not what they wanted me to find. They wanted me to find angle C1. So therefore, angle C1 will be equals to angle A, which is equals to 105 degrees. And my reason for this will be exterior angle of a cyclic quadrilateral. So I know that for a fact. So this angle is an exterior, which is equal to the interior opposite there. So I know that for a fact. Some people might want to first find C2 and then use angles on a straight line. Really, it's one and the same thing. C2, you will say opposite or supplementary, find C1, and then you can be able to solve that. But that's a longer route because already there's an exterior angle that I know about there. Another question is in the following sketch, MTS is 50. I can see that. And I know that MT is equal to MS. So already with this diagram, I know that this angle here, this one here will also be 50 degrees, right? Reason being, this will be an isosceles triangle because already I'm told that these two are equal. So that's already 50 degrees as well. And if that is 50 degrees, this will also be 50 degrees because why? They are subtended by the same arc, right? They're subtended by the same arc. This angle there and that angle there, they're subtended by the same arc. And then determine with reasons the size of P. So already I will start by saying S is 50 degrees. My reason for this will be angles opposite equal sides, and since I know that, I will then say that P is equals to S, which is equals to 50 degrees, and this will be angles in same segment, right? And then voila, I've done that particular part. So far we've looked at circle quad theorems where a converse angle is in the same segment, right? That's what we're talking about in terms of a cyclic quad. We also know that opposite angles of a cyclic quad and also its converse. The last one is exterior angles of a cyclic quad and its converse. And so far that's our concept map. So guys, that's what we had for this lesson that we needed to look at. The relationship between a circle and a quadrilateral around that circle and what are the properties that I can talk about. But please remember, the fact that I say it's concyclic does not only make it to be that makes it a cyclic quad. No, cyclic quad is because of the properties that I just gave you now, the 3 theorems that I just showed you now in terms of the summary. Guys, remember, mathematics is food for the soul. I will see you guys next time. Bye for now.